Statistics Modeling in Finance, Chapter 3, Measures of Dispersion, Page 1, Overview. In this chapter, we will investigate what are called measures of dispersion. In the last chapter, we covered measures of central tendency. We looked at the middle of the pack, where numbers tend to cluster. If we study a number of sales, central tendency will lead to where it is likely that the most probable value lies, as long as there are not significant changes happening in the market, either negatively or positively. It is at least as important to ascertain why individual values differ from the mean, the median, or the mode. All the observations will not neatly fall right around the midpoint of a dispersion. Some tools that we may utilize to analyze this dispersion are the range, average deviation, and standard deviation. We will discuss sample size and sampling techniques. We will illustrate normal distributions and normal curves. There will be a discussion of probabilities. Measures of dispersion can help you judge the disparities exhibited by the distribution of members of a population. They are still part of descriptive statistics. End of page. Page 2, Learning Objectives. Upon completion of this chapter, the participant will be able to describe sampling techniques, describe measures of dispersion such as range, deviation, and average deviation, calculate an average deviation and a standard deviation, describe the characteristics of a normal distribution. End of page. Page 3, Population and Samples. In the last chapter, we defined universe, that's highlighted, or population as, in statistics, a population or entire body of data used to distinguish between a population and a sample obtained from the population. Population is a more generally used term. Then we defined sample, that's highlighted, as in statistics, a subset of a population selected for analysis. Obviously, if we want to know the whole story and receive no surprises, we study the entire population. Why don't we do that all the time? If the population were small enough, that would be the thing to do. However, with large populations, it could be too time consuming and cost prohibitive. If that is the case, be thankful we have a sampling process that can produce statistically significant results. Then we can draw qualified, quantitative generalizations with respect to the universe or population. Let's think about the national elections. Much time and effort is expended in figuring out how people will vote. If you wanted to be 100% accurate, you could contact all 210 million voters as of 2024 and ask them. That's just not possible in terms of time and personnel needed. So, the next best thing is to take random samples. There are companies like Roper and Harris who provide professional polling services. Some universities, such as Marist College, conduct polls. When you hear statements in the weeks before Election Day that candidate A has a lead of 42% to 34% over candidate B with 24% undecided, that is based on polls or samples. Of course, they like to throw in caveats as well, that there is a margin of error of plus or minus 4%. That is based on sample size and the population distribution. We will talk later about how to calculate such statistics. End of page. Page 4, sample size. We stated earlier that a large sample consists of 30 or more observations, and a small sample consists of fewer than 30 observations. With the small sample, the results are hit or miss. If we base a judgment on 3 or 5 or 10 observations out of a population of several hundred, we are taking a big chance. It is certainly possible that we, just by chance, picked our sample from the very lowest or very highest values in the population. It is also possible, but hardly likely, that we happen to pick samples that are truly representative of the whole universe or population. So if we want to be successful in our sampling, the first step is to take a large sample, as many as is practical. The great thing is that once you reach 30, we are getting into pretty reliable territory. If we draw a random sample of 150, the results are not much more reliable than if we use 50. The increase is in accuracy achieved by increasing the sample of 1500 over 150 is minuscule and not worth the effort. The Nielsen ratings are used to analyze how many people watch each TV show each week. Then the networks make multi-billion-dollar decisions to cancel shows, order new ones, or reschedule existing shows based on the results of the surveys. Advertisers make huge decisions based on the ratings of various shows and predictions of how many viewers will be exposed to their commercials. Do you know how many households participate in the Nielsen ratings? Only about 1,400. However, that is enough to be statistically very significant, even though there are 129 million households in the United States. The election polls are based on similarly small percentages of the population, yet statistically are considered large samples. When the networks race to compete to determine who will be the first to call the election, we hear statements like, based on our exit polls from key sample precincts, we are declaring candidate A to be the winner with approximately 53% of the vote. This may be just minutes after the polls close and only a fraction of the votes have been counted. However, there is strong credence placed on votes in certain precincts that have been proven voting records over many elections and have proven to be bellwethers for final raw voting patterns. Can they be wrong? Sure. But with modern technology and computer programs, there are very few occasions like the wrong call on Tom Dewey over Harry Truman in 1948. End of page.